All right, let us summarize what we've learned in today's lecture. So we have learned what a system of n first-order linear what a system of n first-order ordinary differential equations is, and we have learned that any higher-order differential equation can be converted to a system of first-order differential equations. And autonomous systems are those where the right-hand side does not depend on t. Then a linear homogeneous system with constant coefficients is simply when the left-hand side is the derivative of the unknown vector, and the right-hand side is some matrix with constant entries times the unknown vector. Right, and to solve though those systems can always be solved explicitly, and in order to solve it, we need eigenvalues and eigenvectors. With a little bit of caveat, right? So first, it may happen that some of the eigenvectors and eigenvalues are complex. Then this is still going to be a valid formula, only it's going to produce complex valued solutions. So how to convert complex valued solutions to real valued solutions, we're going to learn later. It is also possible that this formula has fewer than n terms. So if A is a non-diagonalizable matrix, then there are fewer than n eigenvectors, and then if that happens, then it's a bit trickier, and I'm not going to cover it in class, but you can read it in the textbook. So for systems of two equations, there are several specific types of a phase portrait of a type of a critical point at the origin, and we can find it out from just looking at the signs of the eigenvalues. So if both are positive, then we have a nodal source. If both are negative, then we have a saddle point. If one positive, one negative, then we have a nodal sink. Then if the question is just to figure out which type it is, we don't really need to compute the eigenvalues then themselves. We can just determine the signs from determinant and the trace. And the main point here is that the determinant A is the product of the eigenvalues, and the trace A is the sum of the eigenvalues. So that's from linear algebra. To sketch the phase portrait, we need to compute both eigenvalues and eigenvectors. All right. Finally, let me review the general theory of systems of linear equations with non-constant coefficients. So with the big warning that usually they cannot be solved explicitly, but still we have a kind of abstract theory. Okay? So we have existence and uniqueness of solutions. So notice that here, if the right-hand side, the matrix of coefficients and the free term g of t, suppose that they are defined on some interval and that continues on some interval, then there is always a unique solution on the same interval. So that is only true. The fact that it is on the same interval is because the system is linear. So if the system is non-linear, then we have still uniqueness and existence of solutions, but the domain could be smaller. Then, if we have n equations with n unknowns, then the solution space, the set of, if the system is homogeneous, then the set of all solutions is a vector space of dimension n. That is still true. So in particular, it means that if you found any n linearly independent solutions, then the linear combination is a solution for a homogeneous system. For a non-homogeneous system, we need to add a particular solution of this non-homogeneous system. Just for your information, that this particular solution, v of t, can be also found by using the variation of parameters, but it's much more complicated because we have a lot of variables here. So it is somewhat similar to the variation of parameters for second order differential equations, but of course it is going to be much more complicated. And then we also have the Wronskian of n vector functions. If we have n vector functions, then we can just put them all together and find the determinant. It is going to be the Wronskian. It is going to be a function of t. So if the original vector functions are linearly dependent, then of course the Wronskian is going to be 0. But if they are linearly independent, then still the Wronskian may be 0. However, if the functions are solutions of a system of differential equations, then they are linearly independent if and only if the Wronskian is never 0. So never meaning with respect to t, because the Wronskian of several functions is a function of t. So by never 0, it means that not for every t it is non-zero. And there is also an analog of Abel's formula and variation of parameters and so on and so forth. But it's just there. If you want, you can read about it in the textbook, but it's just technically challenging. So we are going to skip this material in class. All right. Thank you very much. That's all for